In this video, I'm going to give an overview of streams in Java. In a video that follows this, I'll do a hands-on example, but first let's just understand what streams are. So streams process collections of data, and the data can be in multiple locations. As a matter of fact, the stream doesn't actually own the data, it just makes the data available from another source. Nice thing about stream is that it can skip some unnecessary steps. If you say something like limit, it will go up to that many items and then stop processing. And also it can divide work across several processors, or in other words, work in parallel, which is a really efficient way to maximize our compute. So I have a couple of examples here that I'll get into in a bit more detail in a moment, but I just want to give you an overview of why we want to use streams and what they save. So traditionally we would have a for loop like this if we wanted to sum up something like the value of gas in a tank. With streams, we don't type out a loop like so. We simply chain together a series of operations that will give us the same result. This becomes even more powerful when we want to take a list or a collection of some type and then filter it down to a subset. Traditionally, we'd use an if test with that, but with streams, we don't need to use an if test. Here's another example of a string builder. So in other words, I have some kind of collection like a linked list that has a series of words in it as separate elements, and I want to join them together with a space. So the traditional way to do it would be to create a string builder, have our for loop that iterates over all of the words, appends them together, and then return the final string. But we see with streams, it's much less typing, and it's a much simpler way to go about handling this operation. So streams allow us to describe what we want to achieve without details on how to achieve it. I think this is best explained with an animation. So I have several steps of a stream process here. I have a source of data, I have a series of transformations, and then I have a terminal operation. A terminal operation is something that gives us a result and effectively closes the stream. So you notice that we start with the source of data on one side, the terminal operation on the other, and then the transformation steps in the middle. So I have some collection of numbers here, and we see the first thing that I have, the first transformation is a filter, which is v, and then this is a lambda expression. It looks a little bit goofy with a less than and greater than here, but we have to look at this as one operator called the arrow operator. So we're effectively taking this parameter and passing it over to this logic here. So we say v goes into v less than 8. In other words, the filter is going to say, give me only those items that are less than 8. And as it walks through, it grabs the 1, the 3, the 4, the 6, the 6, and it leaves all of the other numbers. So you see that we've already reduced this set, or this collection, or the stream really, without actually doing an if test. The filter effectively is the if test. Now the next operation says limit 4. It says find the first 4, and then stop processing against that initial collection. So this is where streams can be very efficient, because once it's reached that limit, it doesn't access the other elements after that limit. As a matter of fact, we can use this across processors if we're parallelizing. If we say we don't care which ones they are, but just give us the first 4, or it might be give us the first 40,000 if it's really a high intensity operation of some kind. And we can split that across processors and say, okay, just give me the first 40,000, the first 400, the first 4, whatever we want. Now, after that, we're going to apply a map operation. And a map operation will create a new stream by transforming the elements of the stream that it's attached to. So you see this map operation is going to transform our brownish colored elements to a green color. So, okay, 1 goes over, turns green. 3 goes over, turns green, and I realize now when I look at this, it's a little bit subtle to notice that difference in color, but those are changing color as they go over. So those are our transformation steps, and now we have a series of terminal steps that we can use to return a result. So oftentimes we'll use collect, and we'll say either collectors to list, which will return a list, or collectors to map, which will return a map. List, think array list, map, think hash map. So we could do a collect operation, and it's going to take each of these and put them into whichever collection we specify, and then return that. Now we can only do one terminal operation per stream, but I've listed a couple of other operations that we could do as a terminal operation. If we wanted to use a count, it would simply return 4, because that's what we have retrieved from this collection, or this stream. Now you might say, well, you know it's 4 because we have limit 4. Well, limit really means up to. So there could be fewer than 4. So, that's where a count might be handy. And then find any, well, that's just going to find any of the items from this collection and return it. If we say, okay, once we have filtered this stream down to just what we want, just give me any one of them. It doesn't matter. That's where find any can be very handy. So, a couple more notes on streams. They get data from other places. They don't store data themselves. They work well with lambda expressions. I have a separate video that describes lambdas. If you haven't seen that, I recommend looking at that before getting too deep into streams. And then streams are immutable, so cascading stream calls, like our map operation, will actually produce a new stream at each level. And also, once we've called that terminal operation, we can no longer use the stream. So, some common return values that we'll find in our stream operations. So stream.of is a way we can generate a stream, and also filter is a way we can filter down a stream. Those will both return a stream type. Count will return a long. We know we kind of saw an example of that in that last slide. And then stream.collect, collectors to list, returns a list. Collectors to set, returns a set. And there's several other collectors operations that we can look at as well. And then collectors.joining, this one's really handy if you have something you want to concatenate into a string. In the old days, you had to use a bunch of plus operators to concatenate strings together. But with collectors.joining, it says, okay, take this stream and concatenate everything together, but put this character, which happens to be a space here, between each item as you're concatenating. So a few other common stream methods. We talked about filter, which uses a lambda expression to reduce a stream. As I said, this is where we typically use an if test in a traditional loop, but with a stream, we simply apply this filter operation with a lambda, and it will return a new stream. Count, limit, we talked about both of those. Collect returns results. Get index. This says, okay, get this item in the stream. Get the item at this location in the stream. Kind of like a typical array or array list where you might provide an index and get back that value. Get will do the same thing for us here. Map, we talked about that one. And then for each, we'll iterate over all of the items in the stream, just like a typical loop. A few other less common stream methods. Iterate accepts a lambda expression and simply iterates over it. Parallel's a neat one. Parallel allows you to tell the lambda, hey, I'd like you to do this over several processors. Which again, if you're thinking a high volume of data, something like election results, or something like that where you're crunching a lot of numbers, or census data, anything where you have a lot of data, that is a handy operation to make the most of your compute power. And then generate, this is an interesting one. You pass in a lambda expression and it produces an infinite stream of those results. I could see something like a counter being handy there if you need a unique identifier and you just keep hitting this stream and say, okay, give me a unique ID. That might be handy for that. So lazy processing, I mentioned that if you use limit, it will, once it hits that limit, it stops processing the stream. So it's effectively lazy, which is handy. A lot of these we've seen before: filter, map, limit. A couple we haven't seen: skip. Skip is kind of like the opposite of limit, where limit says stop when you've reached this number. Skip says start when you've reached this number. So maybe we want to skip the first 5 and then start processing. That's where skip would be handy. Distinct, make the elements unique. And then sorted, or sorted with a comparator, returns a new sorted stream. So a lot of the operations we have on traditional collections: sorting, accessing items, making them distinct with something like a hash map. A lot of those things we can do in our streams as well. So to get a stream, there are several options. We can, if we just have a list of things, we can say stream.of, and that will turn this list of comma-separated values into a stream. We can also pass in a traditional array to a stream, or the Java collections framework, the collections we're used to using like list, map, linked list, queue, priority queue stack, they have a .stream method built in that will take their contents and make them available in a stream. Now we know lambdas work well with the stream. There are also some method types that will kind of give us a shortcut that we can just throw in where we would put our lambda. So string to uppercase, uppercase is everything. String compare to, compare strings, double compare, system out print line, and then t new will create a new object of something. Optional type. This is something we use with streams a lot as well. And this is a good way to avoid a null pointer exception, because traditionally, if a variable doesn't have an object assigned to it, and we try to invoke a method on that variable, it'll give us a null pointer exception. Unless we happen to check first to make sure it's not null, which would be a good idea, or prevent it from not being null in the first place. But sometimes we don't do that, and then we get a null pointer exception, and then our program crashes. But optional offers us another way around it, because with optional, we know that the item might have data, might not have data, and we kind of are forced to check for that. So optional, we can say or else, which is a method on optional, which means if there's no object inside of this, then invoke whatever's in this or else part. If present's the opposite, it says if there is something inside of this optional, then we're going to do this activity. So these two are effectively opposites. Or else means we got nothing back and we want to do some kind of operation. If present means we did get something back and we want to do something with that something we got back. Now, if we are actually creating an optional type, of will return a value if a value is present. So let's say that we have some kind of vehicle or something we want to return, then we'll use this of method. Where empty says, okay, there's nothing I can return back, so I'm just going to declare this as empty. Now you can kind of see how these match up. If we create an optional with of, and then later we invoke it as present, we're going to get true. If we invoke an optional with empty, and then later on we say optional.or else, well, that or else part's going to run because there's nothing in that optional type. Now I mentioned some terminal operations. Here are a few more. So terminal operations, count, collect, sum, those kind of things. A couple others we can use, find any and find first. Find any sufficient if we're doing that parallelization across different processors. And we just say, hey, give me any result. Anything that made it through this stream and all of the transformations. Max min, find the highest or the lowest. We can pass in a comparator with the compare to method to determine what's highest and lowest. All match, any match, none match. This returns a Boolean and accepts a lambda. So all match will return true only if all of the items match whatever that lambda expression says. Any match returns true if at least one matches that lambda expression. And then none match returns true if none of them match that lambda expression. Now, because we're dealing with a set of data, we can also group results. So collectors, remember collectors is one of those terminal operations where we say, okay, like we had our collectors.joining, so we could create a string and pass it back. So the grouping function is called grouping by, and it takes a lambda, and it will create a map of list objects. Think about that. Okay, so I said grouping, a map of list objects. So you could have zip code and residence in a zip code. Well, then the map's key would be zip code, and then that would have a collection or a list of residents who live in that zip code. And so nice way to kind of sum that up and put that into a map. And it's interesting that we're using two different collections here. We're using a map where the key is whatever key we're grouping by, and the value is a list of items that share that key. Now, we also have some aggregation collectors, counting, summing in, summing double, summing long, averaging in, averaging double, averaging long. Those are somewhat self-descriptive. So that's an overview look at streams in Java. Once you get the hang of it, they can be quite handy and can really do a lot with a lot less typing than we would traditionally do with a loop, especially if that loop has an if test to filter things down. And we know my analogy about why we like having a small set of code that does a lot of stuff. Because it's like a big house versus a little house. Big house takes a long time to clean. Little house doesn't take much time to clean. I used to live in a big house, and then I moved to a small apartment, and I love it because I get my apartment cleaned in about 55 minutes from top to bottom. So similar with code. The less code we have, the less maintenance we have to do, provided that that code is doing a lot for us. So I hope this video on streams was helpful. I'll have a following video where I'll do some hands-on examples. And as always, I look forward to reading your comments. Thank you.